What? Oh, okay. Good. Can you have your phone? You can take some photos.
Okay, probably we can start. Today we are happy to have Professor Yuval Peres from INSA to give a talk. Yuval is one of the most influential probabilists in the world, and he has made too many contributions we can spend the whole day on. So, but instead of spending time on that, so let's focus on listening to his talk on and work on dynamical population. So let's welcome.
Yeah. Thank you, Fan. Did you hear me? Do you hear me well? Okay. So, good morning. Thanks for coming in so early. And so, when I arrived in Beijing almost 2 years ago, I met with the probabilists in Tsinghua and Zhang Shi from Chinese Academy of Science, and we decided, should we have a joint seminar? And instead we decided, let's do a joint project. And over, I said, almost 2 years, there were many ups and downs, but I'm delighted that this has come to fruition. So I want to thank my wonderful co-authors, Chen Lin, who's here, Chen Lin, and Chen Lin Gu, Jianping Zhang, who couldn't come this morning, Zhang Shi, I don't think he's here right now, Hao Wu, and our chair, Fan Yang. Okay, so so let me start first giving kind of the general background. So a topic of major interest in probability is percolation, where we sample edges of the lattice or of other graphs, and we are interested in a variety of transitive graphs here. Independently, probability P open, probability 1 minus P closed, and then the biggest study is of the clusters of open edges. So it was introduced back in the 50s, but what you see on the slides are pictures by Raphael Cerf of the different clusters of percolation with different parameters P. So when P is Do you hear me? Is it working now? Is it working? Okay. So, and each cluster of open edges, so connected component of open edges, has a different color. And you see on the left, when P is below a half, we have many small clusters. And in a large box, the largest cluster will be logarithmic in the size of the box. When P is above a half, we will see a giant cluster which occupies most of space, and you see that on the right. And when P is exactly a half, which is the critical probability, all clusters are finite. So on the right, I said a giant cluster because we're looking in a finite box. If we look in the whole lattice, then above a half, we will get, in fact, an infinite cluster. And at 1/2, the clusters are finite, but their distribution has a fat tail. So in a large box, we will see clusters that are size a power law of the box. Now, a half happens to be the critical probability in this particular lattice, but the general finding, Broadbent and Hammersley back in the late 50s, is that in any dimension, and more generally in any Cayley graph that, okay, they didn't work in Cayley graphs, but later it was found that in any Cayley graph that is not one-dimensional, we have a critical probability PC where if P is below this PC, we have just only finite cluster. If P is above the PC, we have infinite clusters. And what happens at the critical probability turns out to be very, very interesting, very delicate. And it's known that at the critical probability, There are no infinite clusters in dimension 2, no infinite clusters in high dimension, which is above 11 now, and believed to be no infinite clusters in any dimension, but the intermediate ones are not proved, and dimensions 3, 4, 5 are believed to be especially challenging. Anyway, this is some general background on percolation. Again, above PC, and this is a property of the lattice, there is always a unique infinite cluster, a unique infinite component. This is not true in every graph. So if we take a regular tree and we do percolation, then the critical probability is easy to compute. It's one less than if the tree is d-regular, it's 1 over d minus 1. But at the moment you exceed the critical probability, there are infinitely many infinite clusters. So, and this behavior varies according to the transitive graph, one of the main topics of study. But we're going to look at a different emphasis, which is how the percolation cluster, and later a dynamical percolation cluster, acts as a medium for a moving particle. So this, for static percolation, which is what we have introduced so far, this has a long history and has been studied for a few decades. So I'm not going to cite all the papers, but one kind of standout paper in terms of its depth is a paper by Martin Barlow in 2004 that gave very precise estimates for transition probabilities of random walk on the infinite cluster, or if you work in a finite box, on a finite cluster. Another notable progress was proving a central limit theorem for the location of the particle. The difficulty is that the location, unlike in the lattice where the steps are independent, or in other settings where you have a martingale, random walk on the percolation cluster is not a martingale. Depending where you are, you have a drift that depends on the local structure. So showing that these drifts cancel out was a challenge, and so several breakthroughs by Sidorovicius-Snitban in higher dimension, and my student Noam Berger, together with Biskup in 2007, as well as Matthew Petitsky, proved that the random walk still is diffusive in this setting, so it behaves roughly like random walk in the whole lattice. Okay, so again, this is just background, and now we come to the medium environment we're going to talk about today, which is dynamical percolation. And so this comes from several motivations. One of them in the 90s was one of my co-authors on this topic, Jeff Steiff, gave a talk on percolation, and Paul Maliavan asked him, well, can we use percolation to model lightning if the edges turn on and off according to a random process? And so then with Steiff and Hegstrom, we proceeded to study this dynamical percolation model. And as you can see, this is more than 25 years ago, where every edge has an IID as an independent exponential clock, or Poisson clock. So every edge waits an exponential time, and then turns on or off. More precisely, after the exponential time, it refreshes. So the edge forgets its previous state and becomes open with probability p, closed with probability 1 minus p. Okay? So this is a Markov process on the collection of all edges, where every edge evolves independently. It doesn't look at the other edges. And at any fixed time, so we're going to look at this mostly at stationarity. So we start with percolation, and the edges refresh according to these Poisson clocks. So if I look at this model at any fixed time, 0 or 0.7 or 17, I just see percolation. But it's evolving over time. And so if you want to model inside this system Malyavan's question, you'd ask, suppose I know that in a certain lattice there is no percolation, no infinite clusters when I look at the static percolation. Will there be some time where there is infinite clusters? That was a question studied in the early days of this model. And you see, the question is delicate because if I look at any fixed time, there's no infinite cluster, but there's an uncountable continuum of time, so we can't do a union bound. Fubini argument will tell you that for almost every time there is no infinite cluster. Again, I'm in a setting where I know, so the typical setting, for instance, in 2 dimensions, in higher dimensions, where it was already known back in 97 that there is no infinite cluster for static percolation. That was known. And the question is there an exceptional time where, although I don't see an infinite cluster at any fixed time, could there be an unusual time? These would have to be a set of measure 0 of times where I do see an infinite cluster. So this was the question addressed in the early work, and again with Hegstrom and Steiff, and so this is what I called an exceptional time. So we look at, so theta of p is the probability that a specific vertex, say the origin, is in an infinite cluster. So theta of p equals 0 actually means that there is no infinite cluster with probability 1. Because if there is one, then it can, with positive probability, it would connect to the origin. So an exceptional time, again, arises in a situation where at any fixed time there's no infinite cluster, but at that exceptional time t there is an infinite cluster. And in the first paper we showed that, first of all, there won't be any exceptional time for p not equal pc. So let me explain this a little more. So if p is less than the critical probability, we know there is no infinite cluster at at time 0 at a specific time, and then we extended this to show there is no exceptional times when p is less than pc. Now, when p is bigger than pc, the notion of exceptional times is reversed. So p is bigger than pc, we know there is an infinite cluster, maybe not at the origin, but somewhere. And we showed that there, in this case, there is an infinite cluster with probability 1. For all times, there is an infinite cluster. Okay, so the order of the quantifiers matters here. So with probability 1, so the event that for all times you have an infinite cluster has probability 1 for p bigger than pc. These are actually very easy results. And the interesting case, which leads to not so easy questions, is what happens at pc. And we could prove there that in high dimensions, so at that time high dimensions meant 19, but due to improved technology of the lace expansion, now the method there works for all d greater than or equal to 11 and shows that there's no exceptional times at the critical probability in high dimensions. One case we couldn't decide, and so regular trees we also showed similarly that there's no exceptional times, even at criticality. So the focus is only on criticality because when you're away for critical, there's no exceptional times for all graphs. But the natural case, the case that we see in the pictures, is 2 dimensions. We couldn't do it. And this took spectacular work of first Schramm and Steiff, and then refined by Oded Schramm with Garban and Pete, where they showed that in 2 dimensions, where we know static percolation doesn't have infinite cluster, there are still many, uncountably many exceptional times. So this was in the first paper, Annals of Math, remarkable combination of ideas from probability, discrete Fourier analysis, computer science, and that they showed that there are exceptional times. And then this was refined in work with Garban and Pete, where they used technology coming from the SLE and Smirnov's conformal invariance to show that in the triangular lattice, not only there are exceptional times, but they could pinpoint what is the Hausdorff dimension of the set of exceptional times. I didn't prepare this number, so I can't tell you. Good. No, it's a fancier number. So it's related, but I didn't pair it to this 5/48 exponent of Schramm, Lawler, and Werner for the probability of long-term connection. But exactly the number I didn't come prepared with. Okay, so all right. So this is okay. So I mentioned that, and then I moved very fast on these slides. Okay, so I told you about these results on exceptional times, and striking as they are, they're not the topic of today's talk. Rather, another theme was, well, we have this dynamical percolation. How does random walk behave on it? And this came from several motivations. One was for people in Google or in Microsoft, where I was working for a long time. There was, random walks were heavily used in order to analyze networks, understand connectivity properties, how strong is connectivity, and so on. So massive resources were devoted to random walks on huge networks. At the time, billions of nodes, now even more. And then it was realized that as this network is so big, that as you're walking on it, the status of individual edges in the network changes while you're sampling the network. So when you're in a certain location, the edges right next to you are unlikely to change. But somewhere else, maybe where you've been in the past, the edges will change. When you come back to that point, the environment will look different. So there was a real concrete motivation to have mathematical models for this phenomenon. And of course, mathematical models like the easy model, like percolation, only give us some general conceptual ideas for realistic applications, but they still are important for those applications. So there was motivation. One of our co-authors on this project was Stauffer, Alexander Stauffer, who came from computer science, now is a probabilist, and so he came with this motivation to understand random walk and dynamically changing networks. And of course, there have been other works on this topic from different motivations. So the model here is as follows. So we have dynamical percolation as our environment. Every edge opens and closes at according to Poisson process. But here it's very important to distinguish the rate of change of the environment from the rate of the walk. So a model which is not realistic and also less interesting is when the edges change very fast where the walker is, then in effect you're walking in the whole lattice. So to look at the extreme, suppose the rate of change of edges tends to infinity. Then whenever the walk tries to move, the edge is completely refreshed. So you're really walking on the whole lattice. There is no memory from the past. So that model is not so interesting. And the interesting model, both for theory and for the applications we're interested in, was the model where the rate of change of individual edge is much smaller than the rate of movement of the particle. But because the network is big, or even in the theoretical models infinite, then it still has this change of the network does have an effect. So formally, every edge has a Poisson clock, but now of rate mu. So mu is the probability that in a small time interval, the chance the edge refreshes is mu times the length of the interval. And in general, it's a Poisson process of rate mu, or the time between one refresh and the other has an exponential distribution with mean 1 over mu. So mu is small. You wait a long time, 1 over mu, for an individual edge to change. But overall, something will change somewhere all the time. Okay, so that's the model. And then what does the particle do? The particle has a Poisson clock that we normalize to have rate 1. And so the particle waits an exponential time of mean 1, and then chooses a uniform edge around it in the big graph, in the big lattice, and tries to jump. If that edge happens to be open, it performs the jump. If the edge is closed, it stays where it is. This is still a significant event because the particle now has information that the edge is closed, so this affects the future distribution of the walk. Okay, so that's the model. And so this is connected to the technology to analyze high-dimensional percolation. So there is a process called the lace expansion, which is kind of power series expansion in 1 over the dimension. So it's a perturbative argument. And in order to make it work, one needs the dimension to be relatively high. 11 is not optimal. The threshold for the lace expansion argument to work is 6. So below 6, it really, there's lots of evidence that, and a strong belief that the methods have to break down. But when the method was first created, it worked in higher dimension. The threshold for a long time was 19. And when you apply that method, besides the theoretical analysis, there's a case analysis that's based on analyzing several thousand individual graphs. And so improvement in computing allowed to bring that down from 19 to 11. In principle, it should extend all the way down to 6. It's a computational issue. But dimension. So this is. So this connects to a long kind of study in physics where 6 is believed, and there's some evidence that it's a critical dimension for percolation. So 6 and higher, everything should behave like many things should behave like percolation on a tree. But in dimensions 3, 4, 5, that is not expected to be the case. And there's some evidence for it. For instance, if you study what's called the long but bounded range percolation, where you connect the vertex not just to a bounded neighborhood but further away, then it's proved that all the good behavior that we understand, like on a tree, happens from dimension 6 and higher, and there's a barrier in proving it in 5. So 3, 4, 5 are mysterious in the sense that there's not even a proof there that that there is no infinite cluster at critical value. And in dimension 6, there's still not a proof, but it's believed this is a computational issue and not as concept fundamental. And if you vary in dimension 6, if you change the details of the lattice, it is proved that. But this is. Oh, you can, in fact, I didn't go into it, but so in the original paper at the time, I really devoted a lot of energy to analyzing general trees. And in fact, trees are easier to understand. And in general trees, we have exact criteria in the original paper when they have exceptional times, when they don't. This is completely understood. So tree structure makes things much easier, though it was still substantial work back in the 90s. I'm saying we don't have to assume regular. I'm limiting to regular now just for this talk. But in the 97 paper, we have a detailed discussion of general trees. There are many parameters. But my emphasis now is on the random walk on dynamical percolation, where really to analyze it well, we are using ergodic theory ideas. So we need the graph to be transitive, to look the same for any vertex. And I'm going to emphasize the case of lattices, but we have many theorems that extend to more general transitive graphs. But the lattices have been the traditional test bed of percolation, so I'll emphasize that case. And so as I said, the large network can change while the particle is walking on it, and so this model interpolates between lazy walk on the whole graph. So when mu goes to infinity, what happens is that the particle is just doing a walk on the whole graph, where it actually takes a step with probability p, the p of the percolation. So that is a very simple model. And when mu goes to 0, you go to a model that is complicated but well analyzed, which is random walk on a static percolation cluster. And so varying mu, we interpolate between these models. Because the environment is dynamical, many of the well-established techniques for analyzing transition heat kernels, for spectral methods, electrical networks, don't work as advertised. They need to be modified. Methods that do work involve some ergodic theory ideas because of the time stationarity of the whole model, Lyapunov function methods, martingales, and as I'll mention later, something more specialized, which is the evolving set method. Now, okay, so just these are pictures, 3 snapshots from a simulation where you see the red is the particle and the white are the open states. So I told you mostly the model with bond percolation, but we also do it with side percolation. So this is side percolation on the triangular lattice, but we're looking at it in the dual picture. So it's face percolation on the hexagonal lattice. Every face of the hexagonal lattice is open, that is white, with probability P, and can vary P, and closed, which is blue here, with probability 1 minus P. This is the particle, and these are 2 snapshots on the left and the right of the model, and in the middle is the transition. So we are waiting, a few seconds between the left and the right. In the middle, these light blue edges or light blue faces are those that updated. So, for instance, this one, it was open, and during this time it closed, and here it is closed. Okay, and some closed ones opened during this time, and the particle also moved. But note, it can only move by jumping. It can only move by jumping to an open site. It cannot. And let's see if we can show just before going on to the results, just to show a quick simulation of this by Song. Okay, so this is with probability 0.4 mu. The rate of update of the individual faces is 1 in 100. It's a 30 by 30 lattice, and you see the movement of the particle. Now, when we increase P, let me jump to the supercritical case. This is at 0.7. So again, the white are the open faces, and so there's a lot more space for the particle to move. It moves faster. So maybe that will be enough for the simulation now, and let's go back to the theory. Okay. So these are some of the references, and the slides will be available, so you can look at these are previous references before the present work for this topic. See, it goes back some 25 years. And so one in the paper in 2015, there is a result which is relatively soft, which is that in this model, you still have diffusive behavior. And the key thing will be to understand the rate of diffusion. So, so if you look at time t, the distance from the origin at time t is behaving. If the scaling limit is still Brownian motion, but you can look at it more simply, just the expected, which is what we'll focus on. How does the expected distance squared grow from, so we know in classical random walk, expected distance squared grows linearly in time. And here it still will grow linearly in time, but the coefficient in front, the diffusion constant, is going to be important and will depend on both P and mu, and will have very different behavior depending if we're subcritical, critical, or supercritical. So let me mention, one result from the 2015 paper. So it turns out that the subcritical regime, often in percolation, is easier to analyze. So at that time in 2015, we could only analyze what happens below the critical value. And below the critical value, I told you that the distance squared grows like some constant that depends on mu times t. And in subcritical, this constant is linear in mu. So this is very easy to understand intuitively. So when you're subcritical, the clusters are very small. They're order 1. They have exponential tails. So when the particle is in a small cluster, it can move. Remember, the change of edges is small. So the particle moves fast inside the small cluster, but it doesn't get it anywhere. So the particle has to wait until the small cluster changes for its location to really change. And that waiting time is 1 over mu. During that time, it only moves order 1. So that gives you this idea. To formalize it, you use the idea of a regeneration time. So define the memory of the particle as all edges that it has seen. So the edges that it has crossed or tried to cross and failed. So that's the memory process. So the memory process itself can be dominated by a birth and death chain. So edges enter the memory when the particle tries to cross them, and they leave the memory when they refresh. So, and this process, this birth and death process of memory is recurrent. It keeps returning to no memory. So every now and then, it takes maybe a long time, but it happens with positive density that the particle gets isolated. All the edges around it are closed. And while it's isolated, it's not going anywhere. And edges that it has visited in the past, they eventually refresh. And you reach with some regularity these regeneration times where the particle is isolated and it has no memory. All the memory has been erased. And if you look at the intervals between regenerations, they are completely, the evolution between them is completely independent. So you get a classical random walk or random flight where you jump from one regeneration point and the next one is not neighbor, it's some far away, and the next one, and so on. And these kind of classical random walks have been well analyzed. And so the crucial thing is to understand between these regenerations, how far does the particle go and how long does it take? And how far? Just order 1. How long? Order 1 over mu, and that leads to this behavior, mu t. So once you have the idea to analyze carefully this memory process, this result can follow. At the time, we couldn't do critical or supercritical cases. So that was 2015. Then later, so sorry, the date on this is wrong. It actually appeared a few years later. So later, still with Steiff, but also with Perlasusi, we showed some analysis of the supercritical case. The emphasis in that work was mixing time in a finite torus, but in particular for the rate of growth, we showed it's almost independent of mu. So the result was that the distance squared grows like t up to some power of log mu, and there was also some technical obstacle that we couldn't show it for all time, just from a large interval of time. But let's ignore this technicality and let's say there's some constant that just depends on d and p, and okay, on the interval of time we're looking at, but let's ignore this constant. We have this t, and then what's the dependence on mu? Well, at the time we showed it's a power law of log, but this is just a lower bound. We conjectured both in this paper and in the earlier paper that this log shouldn't be there, so that the diffusion constant should be uniformly bounded below for all mu. And this is natural if you look at the two extremes. When mu equals infinity, it's bounded below. When mu equals 0, you get to random walk on the infinite cluster. So that is also diffusive. So it's natural to believe that it happens in interpolation, but we couldn't prove it at the time. And this is the first main result of the present work with the group of authors here from Tsinghua and Zhanxi from UCAS, where we actually overcame this obstacle and we found a uniform lower bound for the diffusion constant. So the expected distance squared grows indeed linearly in time. So this was, this is not the main result of this paper, but maybe the second most important result. And it is based on refining the earlier method. So the method is this evolving set method, which maybe I'll say a few words about at the end, which was also used in the earlier work, but we were able to do it much more precisely and remove the log terms.
So the notation
pi p is just, this is just the product measure. Every edge, so every edge is open with probability p and closed with probability 1 minus p. That's the initial distribution. In fact, I didn't write it in the slide, but the important thing is that when edges refresh, they get to this percolation configuration. The initial configuration can be, in fact, arbitrary, but that is some further coupling argument. It's convenient to just look at the stationary model where the distribution is just this product law. Okay, in other words, so the diffusion constant here is order 1 uniformly in mu. Okay, I'll say something about the proof at the end. And the most interesting results we have are for the critical case. And this, we were all with my previous projects, we were all kind of avoiding the critical case. It's known to be harder, but in this project we did tackle it. And we have results both for the 2 dimensions. So we need some information on classical percolation, which is available in 2 dimensions due to work of Schramm and co-authors on the SLE and Smirnov on conformal invariance. So we have to use the detailed knowledge of critical percolation to analyze this dynamical percolation, and we get a separation. So this is the exponent that we have. We're not claiming it's optimal yet. We don't know, but we do have a separation of this critical case from the supercritical case. Remember, in the supercritical case, the second moment grew just like t. There was no dependence on mu. But here, there is a power of mu. So there is separation of the supercritical and critical. This is in 2 dimensions, and I'm writing a specific nice exponent for the triangular lattice where we are doing where the conformal invariance is used. In Z2, one can still do an argument using so-called Russo-Seymour-Welsh bounds, and one gets some power, but so we can still separate even in the square lattice the critical from the supercritical case, but this exponent is very, very small, so I didn't write it down. Now it's believed that universality holds for this model, dynamical percolation, as well as regular percolation. So the exponent should be the same, both for the square lattice and for the hexagonal lattice, but that's... So yes, we definitely expect it to be less than 1, but we haven't proved that. So there's various evidence that it's less than 1, but what? Sorry. So no, we have the lower bound, but that just shows it's less equal than 1. Right? So we know it's less equal 1. So we have a lower bound of mu t for the second moment, and this lower bound is applicable for all values of the parameter. So we know that in subcritical, this lower bound of mu t is sharp. In critical, okay, we believe that the exponent is, we have a lot of belief and have a lot of evidence that is strictly between 0 and 1. But the rigorous bounds are what you see here. In high dimensions, we have this second moment bound, so t, and times this mu to half with the extra log factor. Here, we have a lot of evidence that the sharp exponent should be 3/4 here. So very interesting, but, and I'll tell you a quick deviation that when we started this analysis, we realized that the critical case is very hard. So we said, let's try first to do it on a much easier medium on the regular tree, because even on the regular tree, the critical case, was not known. And we struggled with that for a year using some delicate stopping time arguments. And then eventually we found a simplification. We found a nice argument on the tree. And then, we were writing the introduction saying, well, why are we studying this model on the tree? And there's a lot of evidence that the tree predicts well the behavior in high dimensions. And as we were writing, explaining this heuristic in the introduction, we realized actually the argument now in the tree is so nice that it's no longer a heuristic. We can actually make this rigorous. So there is an argument on the tree, which I'm not emphasizing in these slides, but what we did is so we had to retool the paper, and we have actually different papers for the non-amenable case, which generalizes the trees, and for the lattices. But the fundamental idea came while thinking very hard on the tree case, and then we could extend it to these other settings. Here is a summary of the results. So there are results for the non-amenable case. So in the non-amenable case, like a regular tree, or those who know non-amenable transitive graphs like hyperbolic, Gromov hyperbolic graphs, hyperbolic tessellations of the plane. In the tree case or the non-amenable case, the walk is not diffusive. It moves at positive speed. But there is a strong connection between the speed in that case and the diffusion constant in the lattice. And they're actually believed to have the same behavior as a function of mu. And what they do have is essentially the same bounds. So the non-amenable case is on the left. I'm not going to emphasize that. This is just recalling what are the results that we have for the diffusion constant, which can be thought of this. You take the distance squared and normalize by t. This limit exists. So it's order mu in the subcritical case, the same as the speed in the tree. So these are rigorous. So they're the same, the speed in the non-amenable case and the diffusion constant in the lattice. They have the same linear dependence on mu. For p bigger than pc, we now have that also they are the same. So the diffusion constant is uniformly bounded above and below in the lattices, and the same is true for the speed and trees or non-amenable transitive unimodular graphs. And the critical case, the hardest and most interesting, we have these bounds that separate the supercritical case from the critical case, both in the tree. Here it's the speed, and here it's the diffusion constant, and roughly the same behavior, square root of mu with the log correction. Okay, so I want to sketch, some ideas that come in the proof. So one key fact in the lattice, so I'm going to describe the proof in high dimensions, and the proof in 2 dimensions follows similar principles, just using different estimates that are available for percolation in these settings. So let's think of high dimension. So one critical fact we use is the result of Gadi Kozma and my former student Asaf Nachmias, who did it, as the crowning achievement of his thesis. And they solved the long-standing open problem, showing that at the critical value, the probability that percolation reaches distance r, it was already known that in high dimensions the clusters are finite. So you can ask, what is the chance they reach distance r? And the answer is very clean. It's constant over r squared. Okay, so this was conjectured for a long time. It's part of the Alexander Orbach conjecture that they proved. And then much more recently, Hutchcroft, who is a former student of Nachmias and one of the greatest probabilists in the world right now, just a couple of years ago, he gave a general kind of sensitivity analysis in high dimensions. And again, this is based on, I'm emphasizing his paper, but it's based on work of many others as well, and was able to show that the Kozma-Lachmias result extends not just to critical P, but for an interval near P, and the interval depends on how far you're looking. So if P is between PC and PC plus 1 over R squared, then the Kozma-Lachmias estimate still holds for distance R. So the further you want the estimate, the smaller the intervals of P that you can prove it. And this interval is sharp. So of course, you could replace the 1 here by a constant, but nothing more than that. So we use that kind of sensitivity of the Kozma-Lachmias estimate. And so we're going to use it first to estimate the distance squared traveled in a relatively short time interval 0t. So when I say short, this interval, the length of the interval that we will look at will depend on mu. And as we'll see later, it will be about 1 over square root mu. So it's a long but bounded interval. And then we will put together the result for this interval. And before analyzing this, let me actually jump ahead and tell you how we can combine. I'm going to suppose we have some time interval t where we can get a good bound on the expected distance squared. How do we get from that? So I'm going to delay the proof of that and say, how do we get from that to the distance squared in a longer time? We want to understand asymptotics. So a key ingredient here is a beautiful notion due to Keith Ball, which developed further in work I did with Naor, Schramm, and Sheffield, which is the Markov type of Hilbert space and more general spaces. And it tells you the following things, that for if you have a stationary Markov chain on a finite or amenable space, then it satisfies this kind of inequality. So the expected distance squared traveled between time 0 and time kt is going to be bounded by k times the expected distance squared between 0 and t. So it's kind of a triangle inequality for the second moment. It is much more specialized, so it doesn't hold for arbitrary distance. It's just for expected distance squared traveled in a stationary setting when the image space is a Hilbert space. There are other spaces, LPs, and other spaces for p bigger than 2, which have this Markov type property. But here we'll use it in the simplest setting, which was already known in a different language to Keith Ball in '92. So this kind of estimate allows us to go from a fixed time interval to any time interval and bound the second moment. So then we just need to choose a good time interval where we can get a concrete estimate using known kind of percolation methods. So, okay, so let's do one actual computational proof. So hang on, it's just 2 pages. It's not. It just uses the ingredients we discussed. So we take a time t which is going to be smaller than 1 over mu. As I said, it will be about, in this application, about 1 over root mu. But okay, so you take this time and define a new process H, which are the bonds or the edges that are open at least once during the interval 0t. So the bonds that are open at time 0 is a percolation with parameter p. So those that are open at least once in 0t is supercritical percolation, because a bond could be closed at time 0 and open sometimes later. But the parameter of this percolation is bigger than PC, but not much bigger. It's bounded by PC times 1 plus mu t, because the edges open at rate mu, or rate proportional to mu. So we will be able to apply kind of Hashcroft's variant of the Kozma-Lachmias estimate to this type of percolation. Now, okay, so now if the particle, suppose that at time 0 the particle is at the origin, look at the cluster that it's contained in this enhanced percolation H. So if this cluster has diameter less than 2 to the k, then of course the particle cannot go further than 2 to the k in this time interval. So that's what's written here. If 0 connects to distance 2 to the k minus 1, but not to distance 2 to the k, then the distance traveled is at most 2 to the k during this whole time 0t, because we looked at the union of all edges that are ever open during this interval. Okay, so it looks kind of crude, but it becomes relatively sharp by choosing carefully the time t. And I said, what's the chance that 0 is connected to this boundary if mu t is, say, order 2 to the minus 2k, then we can use the Kozma-Nachmias extended by Hutchcroft estimate to give a bound on this probability. So it's 1 over distance squared, so about 2 to the minus 2k. And we put these ingredients together. So this is, the one calculation I'm showing. So the expected distance squared from 0 to time t, we can divide it according to how large is the particle in this enhanced percolation. And so we partition into those cases, and just a finite partition. And then there is a case when the cluster is very big, and this is going to be, so this is some capital K. And for the small case, we use, so this is the one-arm estimate. It gives us this 2 to the minus 2k, which cancels with this 4 to the k. And then for the large cluster, we use a general bound. So this is a variant of the Karn-Varopoulos bound. So Karn-Varopoulos gave first Varopoulos and then refined and simplified by Karn, gave back in the 80s a remarkable bound for the long-range transition probabilities of Markov chains. And in particular, that bound in the case of lattices implies that for any subgraph of the lattice, the expected distance squared traveled by time t is at most t log t. Very general. So of course, on the whole lattice, we know that the expected distance squared is t. But you can choose subgraphs of the lattice which are a little bit faster, but not more than an extra log. So this is classical from the 80s. And there was a different method of proof of that by Davies. And that method of proof was extended by Buckley in 2011 for the dynamical case. So suppose that we don't have a fixed graph. We have edges that open and close, not according to Poisson process, according, your enemy is opening and closing them. You cannot make the random walk much faster. So the expected distance squared is at most t log t in any kind of dynamical setting, even if the edges are chosen by an adversary, as long as the adversary doesn't know where the particle is. So the adversary tells, open this edge, close this edge, but he doesn't see the particle. And however he does, he cannot speed up the particle more than a log factor.
The adversary is trying to speed up?
Yes. So because we're trying to get upper bounds on the distance. So the adversary is trying to speed up, but the most he can get is t log t. And then we have the probability of a large cluster with 2 to the minus 2k. So when we put this all together and choose that capital K, we get this bound, where this capital K will be logarithmic in time. And so the expected distance squared divided by t, we divide by t, we get this thing where this K is essentially log t. That's the number of summons we need logarithmic. And now remember that this t, because of the Markov type argument, we can choose whatever t we like, get a bound, and then it will extend to an asymptotic bound using Markov type. So we just optimize this right-hand side to choose, t is u to the minus half to get this bound. And this is the bound advertised for a fixed t. And as I mentioned, so this is the Karn-Varopoulos bound, this type. And there was a more different argument for it given by Davies, which turned out to be extendable by Buckley to this dynamical setting, which gives the t log t, which we need for the. So in the case when the cluster is small or medium size, we bound the distance traveled just using the size of the cluster, and we have good estimates for the different probabilities. When the cluster is very big, we say, well, we know this is a rare event, but also on this rare event, we don't want the particle to move too fast. So that's where this bound comes in. For the rare event where the cluster is very big, we still have this T log T bound. And putting them all together gives the result. So, okay, so, all right. So for critical planar percolation, oops, I'm jumping too fast. For critical planar percolation, the argument follows similar ideas, just using different estimates that are available in 2 dimensions. So here, the result conjectured in physics for a long time and proved by Lawler, Fromm, and Werner is that the one-arm estimate is this 5 over r to the minus 5 over 48. So that's in 2 dimensions in the triangular lattice. Again, it's believed to hold also in Z2, but still not proved in Z2, but it's proved in the triangular lattice at the critical probability, which is a half. Probability connection distance r scales like this, 5 over 48 plus correction. And then there is something called the correlation length. So there is, for every p, there is a distance where you cannot tell the supercritical percolation from the critical percolation at that distance. You have to go further to tell them apart. And more precisely, there are results, and there's a wonderful survey by Pierre Nolan, who's now in Hong Kong, that explains how one uses the SLE techniques to get the correlation length in 2 dimensions to be p minus a half to this negative power. So as p gets closer to a half, the distance in which supercritical and critical percolation are mutually equivalent, that distance grows as p converges to a half. Anyway, so this plays the similar role to the Hutchcroft estimate I told you about, while this plays a similar role to the Kozma-Nachmias bounds. And then we can affect the same kind of argument. So finally, in the last 4 or 5 minutes, I want to tell you one thing about this evolving set method, which would take a whole hour to fully develop. But this is a method which was first invented in some special setting by Diaconis and Phil, and then the isoperimetric power was found by Ben Morris, and in a paper I wrote with him back in 2003. So the evolving set is a random set that you can use for any Markov chain, and it describes where the distribution is. So, if you look at the distribution of a random walk, of course, it's not indicator of a set. It's it's some measure, but this measure has a layer cake representation where you can write it as an average of indicator functions. And these indicator functions can be thought of as random sets that themselves evolve according to a Markov process. This is the evolving set method. Again, I can't say more about it, but there is an exposition in my book with David Levin on Markov chains of this evolving set method. And the advantage of this method is that it works also when the transition probabilities change from one step to another, as long as you always have the same stationary distribution, which happens in this case. The stationary measure is always the uniform measure here. And so this evolving set describes the location of the walk in the following way. It's a random set, and there's some rule for how to update it one step at a time. So you pick a uniform variable, and you add to the set all the vertices where the transition probabilities into the previous set is bigger than a random threshold, this random threshold U. But the important thing to remember about this random set is that if I take this random set and sample a point uniformly from it, then it's the same as looking at the random walk. So this is a kind of duality that was first noted by Diaconis and Phil in 1990 and fully exploited, in my work with Ben Morris. And okay, we have just a couple minutes left. Let's try to see this simulation. Where did this go? Okay. Up, evolve. So here we're trying to show. So this is the same model, but so this is the dynamical percolation as before. The white is open, but the yellow set is this evolving set. So although we see where the particle is, you could at any time erase the particle and sample a fresh point from the yellow set, and this will have the same distribution as the location of the particle. So this was at 0.4, and I'll show it, for the supercritical case in contrast. So in the supercritical case, the evolving set grows much faster. So in order to show the rate of escape of the walker, it's enough to show that the evolving set grows very fast. Because if it grows very fast, it cannot be confined to a small ball, so the location of the walker is big. So how do we show the evolving set grows quickly, in the last minute? So the idea is to use isoperimetry to say that the evolving set has a big boundary. Well, we need a big boundary of open edges or open faces. So how do we get a big boundary? This evolving set, in general, what it looks like is it involves full. So this is used in the supercritical case to get the lower bound, the uniform lower bound for the speed. So the evolving set will swallow, a bunch of small clusters, and those will not give you any boundary. So to get a good boundary, you have to look at how the evolving set intersects the infinite cluster. And you want to say that the evolving set has a big intersection. A constant fraction of the evolving set will be in the infinite cluster. Sorry, let me go just close this and finish in 1 minute. So we want to show that a big part of the evolving set is in the infinite cluster. And this we can do because when we take the evolving set, sample a random point, that's like the random walk. And we know that the random walk has a fixed positive probability by stationarity of being in the infinite cluster. So using this duality between the set and the walk, we can infer that a constant fraction of the evolving set will be in the infinite cluster. Now, this constant fraction is then a large set inside the infinite cluster. And luckily for us, Gabor Pete, one of my other former students, in 2008, proved a very sharp isoperimetric inequality for large sets inside the cluster. So he said if you have a set which is larger than log n and is contained in a box of radius n, then its boundary, and it's inside the percolation cluster, its boundary inside the static percolation cluster behaves the same as in the full lattice. So it's like the volume, at least the volume to the power d minus 1 over d, same as the perimeter. So this bound of Pete we can use for the intersection of the evolving set with the cluster. And that gives us enough growth to apply the existing isoperimetric bounds that involve the evolving set and prove the supercritical case. So let me finish with a slide of at least indicating 2 open questions. So one is, in the critical case, we found a nice bound which separates the supercritical case from the, in the critical case, we have a nice bound which separates the critical case from supercritical, but we don't know what is the sharp exponent in the critical case. I believe, I don't know if all my co-authors believe, but I think we believe that it will be the same as what we predict on the tree, namely 3/4. So the diffusion constant we believe should be mu to the power 3/4 in high dimensions. So in 2 dimensions, I don't even have a belief right now, but I think we can develop a heuristic, but we haven't done that. But in high dimensions, we have strong heuristic reasons to believe the distance squared grows like t times mu to the 3/4. But we have a bound of t times square root of mu. And the second question, which is in a way more embarrassing, and this was asked already 9 years ago, what are the, it seems that the rate of diffusion should be monotone increasing both in p and in mu. And of course, all the bounds we have have this feature that they're monotone in mu and p. But whether the actual diffusion constant is monotone in mu and p, we can't prove. And none of the people working in this area have been able to prove it. The same problem, even more embarrassing, the same problem is still open even in the tree for the speed. So show that the speed is monotone in p and mu for random walk and dynamical percolation. That would be actually very useful because when mu goes to 0, you get random walk on a Galton-Watson tree for which the speed is known since 1995, and that's my work with Russ Lyons and Robin Pimentel. So if we could have monotonicity in speed and mu, we would be able to compare the speed to that of the Galton-Watson trees because percolation on a tree leads to a Galton-Watson tree. So, but we don't know these monotonicity in either setting of the tree or DD. So that's a challenge for all the ambitious, talented young people here. Thanks for your attention.
Okay, thank you for the great talk. Any questions?
Yes, yes, and so so for static percolation, where the techniques have been developed for a longer time, I mentioned that the location of the particle is not a martingale. So it means that the geometric location is not a harmonic function, which you see. But all the proofs are based actually on using harmonic functions. So you take the lattice and you correct it. So you move the location of the vertices. Instead of being on the lattice, you keep the same graph structure, but you move the location of the particles. So I didn't bring, there's some beautiful pictures of this. So you move the location of the particles, retaining the graph structure, but in such a way that now the random walk becomes a martingale. So it's really a harmonic embedding of the lattice, of the percolation cluster inside the lattice. You find the harmonic embedding of that in RD, and that's the key to then using martingale techniques to analyze the walk. Here, in this case, for the dynamical case, we are not yet using harmonic, superharmonic, subharmonic functions, but they should appear in the next stage. So thank you for the suggestion.
Okay, more questions?
Yes.
Maybe it's the same question, but how does this percolation compare with diffusion? Like, is there like a basic comparison?
Diffusion. We're looking at diffusion in an irregular medium in a way, right? So,
Yes.
So maybe can you explain what you mean by diffusion?
Like percolation, you have this it's just a random walk, right?
We're doing a random walk on the percolation cluster, right? So or on a dynamical percolation cluster.
Okay.
So we are doing, so it's a diffusion in an irregular medium, but we're hoping that somehow the randomness cancels, although you have a local drift where you are, but over time, sometimes the drift is to the left, sometimes to the right, it should cancel. But the exact form of the cancellation gives the diffusion constant, how it depends on mu and on p.
Okay. And do the shapes of the clusters come into play? I guess the isoperimetric inequality is
So
like the
so again, what comes in, especially for the supercritical case, is isoperimetric inequality for subsets of the percolation cluster. And let me emphasize that this isoperimetric inequality only holds for sufficiently large sets. So if I look in the box of size n, I will find little places where the supercritical cluster has little pipes with bad isoperimetry. So there are very small paths which are just connected to the cluster in one point. I don't see chalk, but there is chalk over there. Yeah. So see if you have, yeah, color is fine, right? So you have kind of the main body of the cluster, but then the cluster does have various filaments that get out of it. And these, if you look at this set, it has very bad isoperimetry, right? But what Gabor Pete says, if you look inside the box of size n, then the sets with bad isoperimetry are just of logarithmic size. If you look at anything which is a power law size, so it cannot, it has to cut a piece of this, and then it has a large boundary. How large? In fact, as large as you can hope for, which is the behavior in the lattice is volume to the d minus 1 over d. So that lower bound we have in the lattice, which is the same as the lower bound you have in the continuum, still holds inside the percolation cluster as long as you are not focusing on sets which are too small. So when you look at the evolution of the evolving set, it actually can start very slow because initially it might have a intersection with the infinite cluster that has bad isoperimetry. But this slow period is relatively short, and once it gets big enough, it really occupies a big enough chunk of the infinite cluster that the Pete estimates can be effectively used, and so it has to grow quickly.
Thank you.
More questions?
I found there is only one probability P. That P for involving probability. So
P is the percolation probability. So
yes, so it is the same as the original percolation.
Yeah, so the P is the same as the original percolation.
So if they are different, I mean, if the original percolation is different, the P for original percolation is different from this involving P, where it happens.
So the important thing is what happens when you refresh. So as I mentioned briefly in the beginning, we actually have a coupling argument that says that you can start from an arbitrary environment, like all edges closed or all edges open, and this will affect things for a short time, but the asymptotics are the same. So the asymptotics really just depend on the probability an edge is open when it refreshes. That's the important P. Starting at the same P is convenient for stationarity arguments. So we actually do most of the analysis in the stationary setting, and then there's a separate lemma that says from any environment, when you start, you eventually couple to the process with the stationary environment. So the particles initially, can behave differently, but eventually enough of the memory gets forgotten, and you can just assume that you started in the stationary. So this is, some non-trivial proof, but it shows us that we can really focus on the case where the P, initial P, and the P when you refresh are the same.
Okay, thanks.
More questions?
Is there a relationship with the speed of light in various medium, and in particular in random medium?
I hope so. We haven't investigated. So as I mentioned in the beginning, the original motivation for the process came from Maliavin suggesting to use this to model lightning. So, but we haven't pursued any of this kind of physical connection. So I don't have anything intelligent to say about that.
More questions? So if not, let's thank the speaker again.
Thank you for coming.
See whether we can work on something interesting.
Yes.
穹苍广而恒千，物合多容，星云璀璨，黑洞